unfortunately, our current understanding of those emissions and appropriate and effective controls is incomplete. We're not there yet. The recent paper in Nature by Deducci that Lisa mentioned in her slides examined the role of both in-state and out-of-state pollution on mortality, pretty much the very tip of the health effect pyramid that they talk about of health effects, and a pretty dramatic effect. But you can guess that if it's having a reflection on mortality, then it's also having an impact on all of the things that come under that in a health pyramid, things such as hospitalizations, emergency department visits, use of medications, and just days with symptoms and lost work. So there's a cost, and that's the economics of the health impacts from these types of pollutants. The other thing that's the message from that for our state is that while some of the deaths that were looked at in that paper were attributable to the New York State emissions, in-state emissions from what we have, more of them were attributable to emissions from upwind states, a situation the authors called imported death. This means that our work related to the prevention agenda and the Health Across All Policies initiative to improve the health status of New Yorkers through increased emphasis on prevention, and with its focus on New York State policies, is that much harder. It also magnifies the importance of how energy policy choices in New York State should not ignore the impact of any increased particulate or other air pollutants to reach a carbon neutral goal. The economics and the sustainability of making energy choices that increase disease burden is something we really have to look at very closely. And hopefully this is exactly the group that can look at that. We want to make the wisest choices possible. Thank you.
Great, thank you very much, Pat. A couple of takeaways for me is, I think we all know, but it's always good to restate, is that not all renewables are created equal, particularly when it relates to health impacts or disease burden, as you talked about, and that there's a very wide range of those impacts from losing a little bit of work or staying home for a day all the way to a visit to the emergency room with real dire consequences. So thank you very much for jumping onto that and sharing that with us. And before I introduce our last speaker, I just want to remind you all, right now I've got Jared in the queue, and so go on to the webinar and raise your hand, drop a comment, send a note to Mikhail on the email she sent you earlier. However you can get us your thoughts and get in the queue. After we hear from Richard, we're going to open the floor to a conversation. So Richard Carlson is with Pollution Probe, and he's going to talk with us about the future of natural gas and renewable fuel trade-offs. Richard, welcome to the conversation.
Good afternoon. Thank you for having me. I hope you can hear me.
I hear you wonderfully. Thank you.
Excellent. Well, let's move to the next slide, please. For those of you who don't know about us, and as I'm talking to most people in New York, I imagine you don't, I work with Pollution Probe, which is one of the oldest environmental charities in Canada. We're over 50 years old. And we just completed a report looking at what the potential future of natural gas could be in Canada in a low carbon energy system. This project was supported by the gas distribution industry here, and they're listed there, 4 gas distribution companies in various parts of Canada, as well as the Canadian Gas Association. And we held 2 multi-stakeholder events in order to get input for our report. And the driver for really looking at natural gas is one of it is policy in Canada, which includes, we have federal carbon pricing as well as a low carbon fuel standard, as well as provincial policies as well. Can you move to the next slide, please? And of course, most of you are aware of the large role of natural gas has, and particularly in heating, which has come up many times in this afternoon. But I think it's good just to put it into comparison. So this compares natural gas used for heating in Ontario, Quebec, and New York. I've chosen these 3 jurisdictions, well, New York, obviously, because I'm talking to people in New York, and the other 2 because they are close to New York and have similar climatic concerns in Ontario and Quebec. And we can see there's quite a bit of difference, and in Ontario and New York, it's relatively similar in terms of the huge role of natural gas. While Quebec has 90% of its electricity, 90% of its heating is supplied by electricity, primarily through baseboard heaters, baseboard resistive heaters. Can we move to the next slide, please? And that kind of looking at that and thinking about the role of gas, thinks about the role about how difficult it'd be in replacing gas. And this figure kind of somewhat demonstrates it. This is from Enbridge Gas, which is the gas distributor in Ontario. And it compares gas and electric demand in Ontario in 2015. What we can see is that natural gas demand, of course, peaks in the winter, whilst electricity demand peaks in the summer because of the large air conditioning load we have in Ontario, which would be similar down in New York State as well. And so what we would see is that if we were to electrify a lot of this natural gas demand in Ontario, that would require massive amounts of infrastructure. And just to put that into comparison, I've showed you on the previous slide that Quebec relies on electric resistive heaters for 90% of their electric load. And what we have seen is in Quebec, peak demand in Quebec is 36 gigawatts. Their lowest electricity use is 12 gigawatts. In comparison, Ontario, which has almost double the population of Quebec, our peak electricity demand is 21 gigawatts. So you can see that if we were to replace that gas demand with straight electrification, that could rapidly increase our electricity load. And even with cold climate or sort of heat pumps, they would not work at the peak heating demand times in Ontario, because generally around I'm going to be using the metric system here, minus 10 to minus 15 degrees centigrade, they stop being very effective, which while in January and February in Ontario, we regularly get heating demands at well in the minus 20s. So that would require, if we were to meet the peak heating demand with electric resistive heaters, that would still require the exact same electricity build out that would be required. And I think this would be particularly expensive in urban areas because of the need for grid reinforcement. So it's not so much on the generation side, I think the cost would be, but primarily on the network side. So if it's electrification would be difficult and expensive, what are the options? Can we green that gas rather than replace it? So we move to the next slide. So the one area to look at that has been brought up many times is looking at the biogas, particularly renewable natural gas, primarily from organic waste. There's two main types of renewable natural gas. The most common is what I've referred to as coming from wet waste. That is such as agricultural waste or landfill and wastewater treatment plants. This has the added benefit of capturing the methane that would normally be emitted. So that also does help reduce emissions. There's a second opportunity of gasification of biomass to produce renewable natural gas. Now that is very expensive and energy intensive and is not done at any large scale yet, and does require large amounts of waste wood as well if you're going to be gasifying waste. Now the problem with the supply of renewable natural gas is if you're looking at the current technologies, so the wet waste one, including agricultural waste or landfill and wastewater waste, generally what we're seeing in all the reports, if you look anywhere in the world, is it maxes out about 10% of current natural gas consumption can be met with renewable natural gas. And that we've seen in Ontario, it's a bit lower, 5 to 6%. Quebec has around 12%, but they have a much lower gas demand. In European projections, they say 500 terawatt hours of gas. Everyone likes to use different terminology here, so we're using petajoules, terawatt hours, and BCF. But in Europe, they say about 9% of their gas demand by 2040 could be met by renewable natural gas. And the study by the National Grid for New York says that 193 BCF per year could be met using renewable natural gas. Again, that's about 10% of total consumption. And so why is that? If we move to the next slide, we can see that RNG has limits, and part of that limit is just the supply of source. So regardless of the cost, we can see the cost of the MMBTU. Now, if you start looking at municipal solid waste, wastewater treatment plant, or agriculture and dairy waste, is that there is just not enough of them, of the supply, in order to produce that much gas. But on the landfill gas side, there's a bit more scope for increasing depending on the price. But even then, you are going to be severely limited, particularly as we start getting better in terms of waste diversion. So that's going to always limit the amount of RNG that's available. And as a further example of the potential, there's the National Petroleum Council did a study looking at the amount of renewable natural gas in the US, and they came out to about 4.7 TCF a year. So that's, again, just a bit over 10%. Okay, next slide, please. So if we start looking at RNG, and one of the main areas supply is limited, one of the options that people are looking at is hydrogen. And hydrogen has received a lot of attention recently. $1.5 billion globally was invested in hydrogen in 2017. The hydrogen could be blended with the current gas system. It could replace the gas itself, a 100% hydrogen system, or you could be used to create synthetic methane. Now, how do we get that hydrogen is very important. There are two different sources for hydrogen that I'm going to talk about here. They're very low carbon sources of hydrogen. There's what we call green and blue hydrogen. Green hydrogen comes from electrolysis using clean electricity. And for that, I would include renewables and nuclear. There may be different definitions in different jurisdictions, but non-emitting sources of electricity, the electrolysis using non-emitting sources of electricity, be that renewables or nuclear. While blue hydrogen, it comes from natural gas, steam methane reforming with natural gas. But in blue hydrogen, the carbon that comes from the steam methane reforming is captured using CCS technology. So it is called blue hydrogen. So it is low carbon, even though it is from natural gas. Costs for these are, of course, naturally going to be a problem, particularly with the industry starting out. And the most SMR is probably the most near-term technology, and we're still looking with CCS at around $12 to $13 a gigajoule currently, about $1.5 a kilogram in US dollars. So it comes out to about $12 to $13 a gigajoule, which if you think delivered natural gas in North America is probably running at about $2.5 to $3 a gigajoule. That is still not competitive. With electrolysis, with renewable energy, the price very much depends on the inputs of the renewable electricity. And one study that we've done looks at, in British Columbia, they could get it for around $32 a gigajoule. BC is blessed with, like Washington State, its neighbor, is blessed with large amounts of hydropower and relatively expensive hydropower. So that would be on the low end, I would imagine. Bloomberg New Energy Finance says we need to get the cost of green hydrogen down to around $4.5 a gigajoule, which works out about $1 a kilogram. And they see that as being possible by 2040, depending on the reduction in cost of renewable electricity. And so there's also needs to understand the way that hydrogen acts into the gas grid and whether or not the gas grid can accommodate large amounts of hydrogen. And there are some pilot projects being undertaken at the moment looking at that. There's, most particularly in Europe, there's a new project that just started up in the UK called HyDeploy, where they're testing a 20% hydrogen mixture by volume. Again, hydrogen has a lower energy content than natural gas. So a 20% hydrogen mixture is about 10%, is about a 10% by energy content mixture. And that'll be testing up. That'll be starting this year. There's the GRID program in France, northern France, and they're testing up to a 20%, again, a 20% blend of hydrogen. There's a study done by the US National Renewable Energy Laboratory says that about 20% blending is feasible. But again, it would be up to you'd have to assess the local gas grid and discover what kind of equipment they have, what kind of pipes, especially cast iron pipes cannot work with hydrogen because there's far too much leakage. So, well, modern pipes can at least accommodate up to 20%. So you'd have to do that testing to see whether or not hydrogen can be blended in there. There are two projects in Canada that are being proposed, and Bridge Gas has an electrolysis program in Ontario, and they're proposing to blend 3% by volume, 2% by energy content. And Fortis BC is proposing a project up in northern BC powered by wind power, electrolysis project powered by wind power. And that is to help meet provincial targets for them to provide renewable gas in there. To the province. And another option with hydrogen could be the creation of synthetic methane. I know Macy brought that up earlier. And the idea would be taking the hydrogen and combining it with CO2. So you're creating a synthetic form of methane, which could be injected directly into the current gas grid without any concerns. Of course, that would have, in order for it to be carbon neutral, you would have to look at the hydrogen would have to come from green electrolysis, and then you'd also have to either have air capture the carbon or using carbon capture and storage at a biomass plant. And there's a pilot project in Germany where they're capturing the carbon from a biomass plant and they're combining that with hydrogen from a local wind farm to create synthetic methane. So it's a very small pilot project, I think 4.5 megawatts, but it is starting to be done. It is potentially to be done. If you can move to the next slide. Of course, all this is kind of the most important part here is we have to get that New York wants to get to net zero by 2050. So we have to also look at the carbon intensity, GHG intensity of these different types of gas. Green hydrogen is 0 and clearly comes on the top. And of course, waste from agricultural, by renewable natural gas from agricultural waste is even better and at almost negative $250, negative 250. So that has significant. These are I should put the grams of CO2 per megajoule. That is because you're capturing the methane that would normally be leaked out. Hydrogen from SMR is quite high, and even if you have SMR and combined capture and storage, which is SMR plus CCS on this graph, you see there still are emissions because CCS generally can only be expected to capture up to 90% of the GHGs. And RNG does come in higher, but so you have to compare. But this also looks at is better than releasing the methane to the atmosphere, and so whether or not that accumulates on an accounting basis. And the next slide. And of course, this cost is always important. These are cost in Canadian. These are in Canadian dollars. Sorry, I didn't have a chance to move this to US dollars. So just take 25% off the numbers. This is cost in dollars per gigajoule. Looking at the different RNG options, the hydrogen options, conventional natural gas, and renewable electricity. And I think this kind of comes to a very important consideration is, yes, the costs are always going to be higher than current natural gas prices, which current natural gas prices in North America are so low, pretty much any option is going to be more expensive. But if you're going to be comparing costs to what? So cost of natural gas, nothing is going to win. But if you start comparing renewable low carbon gases or renewable gases with renewable electricity, well, then the cost can sometimes be comparable. If you're looking at, say, for example, the price of utility wind or utility solar, that is already competitive to some renewable natural gas options. And depending on the feed source that you have, could even be lower than a lot of the renewable electricity options. We're just so used to having cheap natural gas, so we're comparing the options compared to natural gas, which is going to be next to impossible. Of course, electrolysis could drop quite a bit, significantly lower, but that will be that will be due to the cost inputs of the renewable electricity dropping, so it will kind of offset slightly as well. But that could be competitive. It could be competitive on the cost side before you even start looking at the resiliency costs. Next slide, please. But instead of looking at gas versus electrification, maybe we should look at trying to bring all this together. Maybe this is me just playing the stereotypical Canadian and trying to make a compromise with everything. And that would be hybrid heating, which would be using air source heat pumps or other electric heat pumps, plus gas-fired backups. Initially, that could be used with gas-fired, and then as the gas system itself becomes decarbonized and having lower, that could be a zero carbon option as well. That is one area, but of course, as was already brought up in earlier discussions, the cost of running dual equipment can be a problem, and also we're going to have the cost of whether or not running a natural gas grid with low throughput is actually possible. So if we are going to be looking into hybrid solutions, what is the cost of being able to run a low throughput natural gas grid that we already have? And that could be difficult. Reduce and substitute is probably going to be one of at least the first thing we can do, which is reduce the amount of gas that we need and then start substituting it. And if you really think about green hydrogen and using electrolysis, is that green hydrogen, the production of green hydrogen is in itself a form of electrification. It's just not using electrification at the point of use, it's using electrification somewhere else to produce the green hydrogen that is then supplied through the gas system. So in a certain way, green hydrogen is almost electrification. And we are using both electrons and molecules there at the same time. Regardless, they're clearly that we need to start moving now, and New York has already started doing that. If we move to the next slide, that will just end off my presentation. So the full report can be found online, which we look into more detail on some of these options. Feel free to contact me at any time if you have any questions. Thank you very much.